7 years ago, I made a bet and enrolled in a master's program in biostatistics. At the time I'm reading this, I'll soon be graduating with a PhD and I'll be working full-time as a statistician in a few weeks. So, I guess the bet paid off. And you might be contemplating a similar bet. Is it worth it to get a statistics/biostatistics graduate degree? What kinds of skills would you get out of it? After 7 years of doing it, I have a pretty good idea of how to answer these types of questions. So in this video, I want to give you the bigger picture of what graduate level biostatistics looks like and how everything you learn fits together into a sort of statistical skill tree. If you're new here, my name's Christian and this is Very Normal, a channel for making you better at statistics. Let's get started. Before I started my master's degree, I'd only ever taken 2 statistics courses. This was during a time that I didn't really take school all that seriously. Like with any new game, I started with an empty skill tree like this one. I've imagined this tree to consist of 3 parts: the core, the shell, and the advanced skills. The core represents the key concepts and ideas that are relevant to pretty much any statistical method. It roughly corresponds to your required coursework in the first year. Master's and PhD students often take the same courses or cover the same material, so I don't differentiate between them here. Next is the shell. The shell represents different foundational skills that build on the core and that career statisticians would be expected to know on a job. Some of the skills in the shell might be learned alongside material in the core, but others might build on other shell skills. The core and shell correspond to roughly all the required courses for master's and PhD students. You'd be able to handle basic statistical consultations and basic independent analyses. Beyond the shell are what I call advanced skills. You'd pick up these skills from elective courses or even seminars. I won't go into these in depth, but I still want to show you what advanced statistics looks like. I'm definitely going to miss some specialized areas of statistics in this video, so if there's anything important I've missed, let me know in a comment below so I can gather them for everyone to see. In the end, you're getting a graduate degree for technical skills, so it would be good to know what these skills are. Let's look at the core. I've imagined the core to consist of 3 main groups of concepts and skills: probability, mathematical statistics, and statistical programming. I think of probability as the branch of mathematics that studies uncertainty. Mathematical statistics might sound a little weird to you. You could think of it as the mathematical theory that underlies statistical methods. Finally, statistical programming refers to programming that specifically deals with the application and implementation of statistical methods. As I've said many times on this channel, statistics nowadays is mostly done on a computer. So programming is how we tell the computer what to do. Statistics and probability are often paired together, and for a good reason. Statistics builds on the ideas from probability, so it's impossible to separate the two. Despite this, graduate programs will often make probability a separate course from the rest of the statistical courses. This may make sense from a separation of topics perspective, but I've noticed that it tends to make it harder to see all the interconnections between probability and statistics. Since I'm going for the bigger picture, I'm going to interleave these 2 parts of the core together. Statisticians are in the business of dealing with data. On a surface level, data may just seem like information in the form of numbers, but there's more to it than that. When we collect data, it's impossible to predict what we'll see ahead of time. We might have an idea of what values we might see, but we won't know the precise value we'll see until we try. That is, data are random events, uncertain and unpredictable. Data are random objects, so we need to involve concepts from probability. The main object that we use for random events is the random variable. When we actually make the observation, we'll get a single realization of this random variable. Depending on what our data looks like, these observations may be discrete, aka categorical, or continuous. Random variables have several other objects that can help us characterize them in different ways. First, random variables have functions called probability distributions that describe what data values are likely, unlikely, or outright impossible. Depending on whether your data is discrete or continuous, these functions may look different, but their role remains the same. These probability distribution functions are useful because they let us characterize the random variable without needing to actually observe it. For example, the expectation of a random variable represents a typical value you might see in your data. Expectations are defined in terms of an integral over the probability distribution of a random variable. Similarly, the variance characterizes uncertainty, as measured by how far a random variable can deviate from its expectation. Usually, expectation and variance are what you'd worry about the most in statistics, but in more niche cases, you might worry about higher moments like the skew or kurtosis. While variance describes the uncertainty in a single random variable, we also have a notion of how 2 random variables vary with each other. This is covariance. But usually, we talk in terms of correlation instead of covariance, since it's standardized between -1 and 1. So far, we've just been talking about a single data point, but we all know that we need more data than that to do anything useful. Multiple observations give us a dataset. Typically, we assume that each of these observations in our dataset come from the same underlying random variable. That is, our data is IID, independent and identically distributed. This assumption is required for several important theorems that will come up later. Having more data gives us more information about the underlying random variable, but it brings another problem: presentation. If we've observed n data points, what is the best way to talk about them? I wouldn't want to list out each individual value every time I want to talk about the data. Instead, we condense our data into a single summary value called a statistic. A statistic is just a function of the data. Functions or transformations of random variables are also random variables in and of themselves, so statistics have all the same objects associated with them. A generic statistic is just a function of the data, but different types of statistics have different uses. Some statistics are called estimators. They act as estimates or educated guesses for important values related to the random variables that generated them. Then there are test statistics, which are used to conduct hypothesis tests. Hypothesis tests are how statisticians make data-driven decisions in the face of randomness in the data. Some test statistics are derived from estimators, so these ideas aren't mutually exclusive. For both estimators and statistics, we're interested in characterizing the probability distribution that governs them. We even give that distribution a special name, the sampling distribution. But characterizing the sampling distribution can be difficult, especially when the underlying data can take on so many different forms. Thankfully, there are theorems that give us nice sampling distributions if we're looking at a particular statistic. For example, the famous central limit theorem tells us that the asymptotic distribution of the sample mean is a normal distribution. And the delta method tells us that some function of the sample mean are also normally distributed. We take advantage of these distributions to derive some useful probabilities and perform these hypothesis tests. My board's getting a little cramped, so I'm going to clean up things so we can start back with estimators. I said that estimators are educated guesses, but didn't really get into what they're trying to guess. When we gather data, we typically have a target group in mind of what we want to study, which we call a population. In practice, we can't gather data on everyone from this group, so we collect data from a sample with a reasonable amount of people. Our goal is to learn about a specific aspect about this population. These characteristics are represented by values called parameters. Because we can't observe the entire group, the exact value of this parameter is unknown. So this is the thing that we're trying to estimate from data. We usually model the data from the population as coming from some parametric distribution, where the parameter will completely determine the shape of the function and which values are likely and unlikely. By far, the most common examples are the normal distribution for continuous data and the binomial distribution for binary data. We might be interested in estimating the mean of the normal or the probability of success from the binomial. So now we know what an estimator is. Now we need a way to actually make them. That is, how should we use the data we collect to actually construct the guess? The main method that students will learn is maximum likelihood estimation. It's not the only way of making a guess, but it is by far the most relevant method to the tools that graduate students learn. We construct the maximum likelihood estimator by taking the probability distribution of the data and using it to construct a function called a likelihood. By picking the parameter value that maximizes the likelihood we have, then theoretically, this should be a good guess. And yes, people have demonstrated that the MLE has great properties for an estimator. It's consistent, meaning that the estimator will get extremely close to the true parameter with large amounts of data. It has a nice asymptotically normal sampling distribution with the known expression for the variance, so it's rather easy to calculate probabilities from. And it's asymptotically efficient, meaning that the variance of this distribution reaches the lowest possible value it can take. In a sense, it means that we're making the most of our data and giving ourselves the best chance of making good decisions if we use the MLE. In your courses, it's easy to see the maximum likelihood estimator as just another calculus exercise. For basic problems, the MLE will have a nice exact form, but this won't be the case in general. Instead, you'll need to rely on computers and optimization algorithms like the Newton-Raphson algorithm to get the value of the estimator. There may be other situations that make it impossible to use maximum likelihood directly. Our models might have missing values for data or parameters, but we can turn to the EM algorithm to overcome this problem. Some of the more advanced models you'll learn in the shell are only possible thanks to algorithms like these. I've tried to keep this mapped to the core concepts, but there are so many specific concepts that I've had to leave out just to keep the visual clean. Mathematical statistics and probability form the theoretical background that graduate level statistics students are expected to have. They can give you a proper sense of when a tool would be useful, and maybe more importantly, when a tool is inappropriate. It still remains that models need to be applied to specific problems. This is where statistical programming comes in. To communicate with the computer, we have to use a programming language. Both of my graduate programs elected to teach the students R, since it's wholly dedicated to statistical analyses, but I've also seen Python offered for elective classes, especially for those focused on machine learning. Most people think of statistics in terms of applied statistical tools like hypothesis tests, regressions, and predictive models, but statistical programming encompasses much more than that. For example, I mentioned earlier that optimization algorithms come into play with maximum likelihood. When a statistician is developing a new method, they're the one that has to translate it from the theory to the actual software that other people can use. From my observation, this is actually a weakness of the programs I've been a part of. Statistics students are not often taught good practices when it comes to developing software, but it's really up to the student to actually pick up this extra knowledge if they want to stand out. Statistical programming also plays a role in testing and evaluating new methods, and this is usually done through Monte Carlo simulations, aka simulation studies. In simulation studies, we can control the characteristics of the data through random number generators. Even though the data is random, having control of this process lets us evaluate how models perform in different settings. This is especially useful for seeing and quantifying what happens when our statistical assumptions are violated. Maybe you've been listening to me talk about all these math and programming concepts, and you're feeling a little behind. That's how I felt when I first started my master's, and I used that memory to hit the ground running when I started my PhD. If you'd like to get ahead, but don't know how, then maybe the sponsor of this video, Brilliant, can help you out. Brilliant helps you get smarter every day with thousands of interactive lessons in math, science, and programming. All of Brilliant's lessons focus on hands-on problem solving, which has been shown to be way more effective than learning through passive learning. Brilliant's first principles approach empowers you to develop a solid understanding from the ground up. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/verynormal or scan the QR code on the screen. You can also click on the link in the description. You'll get 20% off an annual premium subscription if you sign up with my code. Thanks to Brilliant for sponsoring this video. This brings us to the shell, the collection of tools that we're taught. In reality, there are an innumerable number of statistical tools out there, but graduate programs have narrowed them down to a small subset that are considered essential for any statistician to know. What I've tried to do is capture the essence of that subset into a tiny map. One of the first things that students learn is basic hypothesis tests. For better or worse, hypothesis tests are how we make informed decisions in the face of random data. We use hypothesis tests to decide whether or not a given state of the world, the null hypothesis, could have reasonably produced the data we saw. The type of data we're dealing with, continuous or categorical, changes the type of test we'll use. If we're dealing with continuous data, you might use a z-test. You might remember that the central limit theorem provides us with the limiting distribution for the sample mean, so we can leverage this distribution to make a hypothesis test. If we can assume that we know the variance of this underlying data, we get the z-test. But more often, we have to estimate it from the data instead. This adds extra variance into the test statistic, which yields the famous t-test. We can also leverage the z-test to perform hypothesis testing on categorical data as well. This gives us the proportion test. For all these tests, we can easily extend them to the case of a two-sample test, where we're comparing two groups. And these are all easily derived thanks to the properties of the normal distribution. For categorical data, we can turn to the chi-square tests and its other variants. These hypothesis tests rely on the assumptions of the central limit theorem to be valid, but real-life data doesn't always let this happen. When this is the case, we may need to turn to a different class of hypothesis tests to allow us to avoid making unreasonable assumptions. This is the world of non-parametric tests. These might require us to ask slightly different questions of the data, but there are well-established one-sample, two-sample, and multi-sample hypothesis tests in this area for both continuous and categorical data. All these tests together can make decisions that cover an impressive amount of basic research questions, and you'll most likely be helping non-stat people deal with them. The output of hypothesis tests is a decision, and we can measure the quality of these decisions in several metrics. One of the most commonly used ones is type 1 error, which is when you accidentally reject the null hypothesis when it's true. When we consider multiple hypothesis tests at the same time, we might consider the family-wise error rate or false discovery rate instead. Since the true state of the world is unknowable, we won't actually ever know when we commit a type 1 error, but we can set a level to define our tolerance for the probability of doing one. Once this level is decided, we want to maximize our power, the probability of correctly rejecting a null hypothesis when it's actually false. Power is mostly used as a planning tool for research designs, but we'll get back to this later. When we're using a test, we want to make sure that we're using the most powerful hypothesis tests that are available to us. Something you might learn as a PhD student is the concept of most powerful tests, which achieve this goal. What you'll learn down the line is that almost all the tests that we teach to statistics students are some form of these most powerful tests. It's important that other people have proven that these tests have these properties, but it doesn't really change much from a user's standpoint. One of the most common types of research questions you'll encounter are about relationships between variables. We want to know if these relationships truly exist, so we often derive hypothesis tests based on the estimated parameters for these models. In general, these are called regression models, and the very first one you'll learn in graduate school is linear regression. Linear regression is the simplest regression model we have, and it forms a useful baseline for learning other models. It tells us how the change in the independent variable are associated with average changes in a continuous outcome, and it can easily be extended to multiple variables simultaneously. We estimate the parameters in a linear regression with the famous ordinary least squares estimators. These estimators are known to have a multivariate normal or t-distribution, which we take advantage of for hypothesis tests. Not only do we have this useful distribution, but another theorem, the Gauss-Markov theorem, says that the OLS estimators are the best we have, assuming the conditions for the theorem are right. But we may have outcomes that aren't continuous, so linear regression won't cut it here. To account for different outcomes, you'll learn about the generalized linear model, or GLM. If you can assume that your outcome comes from a special distribution called an exponential family, then you'll have access to the GLM. We mentioned the normal and binomial distributions earlier, and in fact, they're also exponential families. Exponential families have a ton of other convenient properties related to estimators and statistics, so this is why GLMs are so commonly used. A recurring theme in statistics is the trade-off between realism and simplicity. A GLM is a useful model, but at the same time, it's also a very simplistic one. It reduces the relationship between two variables to a single number. If we want our model to better match the data we collect, then we may need to violate some necessary assumptions for a simpler model. One of the first examples of this in biostatistics is longitudinal data, where a single unit may produce several correlated observations. Ignoring this correlation can greatly hurt our results, so this motivates us to learn more complex models to handle the specific aspects of the data. One might use a GEE or a mixed effects model to account for this correlation. These models can both be seen as further generalizations of the GLM, and they both have their pros and cons. Another example of this realism-simplicity trade-off is in the world of survival analysis. Survival up to a given time point looks like a continuous variable, but it has special considerations we need to account for. It's possible for survival data to be censored, meaning we don't actually observe if someone experiences the event we're interested in or not. If we don't account for the censoring, we'll get biased results. Tools like the Kaplan-Meier curve and Cox's proportional hazard model are the main tools that students will learn in this domain. I mentioned earlier that hypothesis testing plays a significant role in regression analysis. This brings up the question for the sampling distribution for the estimates for these models. Besides the GEE, all of these models get their sampling distribution from maximum likelihood theory. If you're curious, the GEE also has an asymptotic normal distribution, but it's derived from a different method. When most people think of statistics, I think this is what they have in mind: the analysis of data via hypothesis tests and regressions. But in reality, career statisticians are also in charge of designing the experiments and specifying who, how, and what data we collect in the first place. In biostatistics, this is also known as clinical trial design, but the more general term for it is design of experiments. This is the skill set that earns biostatisticians six-figure salaries, so being skilled here will have big benefits for your wallet. The experiment that most people are familiar with is the randomized controlled trial. You might know it as the A/B test. Randomized controlled trials are important because they allow us to make cause and effect statements about the relationship between two variables. Statistical models and more data are not enough to make such a strong claim, and this is why design of experiments is so important. There are lots of other types of experimental designs out there. The randomized controlled trial is actually one of the last experiments that we perform in evaluating potential new treatment. There are many others that have to happen first before we get to this crucial step. First, we have to figure out how much drug is safe to give to people. This is the job of the so-called dose-finding studies, or phase 1 studies. After a safe dose is found, a drug will proceed to many phase 2 trials that will try to figure out if it's actually effective or if there are any side effects that we need to know about. These are distinct from the randomized controlled trial because they're usually concerned with single arms. and not comparative effectiveness. The classic task that a statistician would need to do for an experiment is figuring out how much data we need. While it would be nice to have infinitely many data for all our experiments, we have to live with real-world constraints. So we do sample size calculations to make sure we have enough data to have a strong chance of a successful experiment. Even though it's a key skill, I can really count the number of times that I was asked to do a sample size calculation in grad school on just one hand. Besides sample size calculations, statisticians can also provide advice to other researchers or even companies in designing their own experiments. This is called statistical consultation. Not everyone gets training in design of experiments, so statisticians play a key role in making sure that other people get usable data from their research. Statistical consulting is hard, but it's really exciting to get to work on a wide variety of research problems. These trial designs form what's called the traditional paradigm of clinical trials. Medicines have followed this path of experiments for a long time, but statisticians have also started to develop more modern forms of clinical trials to make the process more efficient. For example, some new trials fuse different phases of the traditional paradigm together. There's something called a seamless phase 2/3 design, which blends phase 2 goals and randomized controlled trials together. Other modern designs, known as master protocols, consider multiple treatments or populations simultaneously. Another form of experiments that statisticians can learn are adaptive trials. These are trials that have pre-planned changes that can happen over the course of the experiment. For example, adaptive trials may have built-in rules to end the experiment early if the treatment doesn't look like it'll be successful, or it can alter the randomization probabilities of the treatment so that promising treatments get more exposure to future participants. Adaptive trials were a large portion of my PhD, so I think they're pretty cool. A common theme among these three sets of skills is that they focus on statistical inference, the act of drawing conclusions on a population based on the sample we drew from it. Aside from that, there's a totally different flavor of statistics that deals with prediction, using models to predict the value of future data based on the values of past data. This is known by a lot of names, but for simplicity, I'll go with machine learning. I didn't get a lot of machine learning coursework in my master's or my PhD, so I'm not nearly as familiar with it compared to inference. That being said, I'm familiar enough with it to at least give you a general overview. Depending on the kind of outcome you want to predict, there are two types of prediction you can do. Prediction of continuous outcomes is called regression, while prediction of categorical outcomes is called classification. Of course, there are different subcategories for each of these prediction tasks, but we'll keep it to these for now. In both of these cases, you gather some data and you use it to estimate a function which will act as your predictive model. There are lots of different types of machine models learning out there, tree-based models, even the simple linear regression, but I won't cover them here, we're just going for bigger picture. We'd like these predictive models to perform well on data it hasn't seen before, and we summarize this performance into a single number. I'll call this generalization error, since I think it's more descriptive than just test error. This generalization error is based off of some loss function that acts as a measure of how good or bad a model's predictions are. In regression, the mean squared error is an example of a loss function, while in classification, you might use accuracy. To get a sense of how well our model performs in unseen data, we might also split our observed dataset into two sets, one to train the model and another to estimate the generalization error. There are also other methods like cross-validation to help give us a better sense of the variance in the estimated test error. While you can estimate the generalization error from a subset of data, in the end, the test error we get is based on the data we saw. We'd still like some mathematical guarantees that our machine learning models will perform well. This is where frameworks like empirical risk minimization come in, the mathematical foundation of machine learning. I thought machine learning was easy before I learned about this framework, and I quickly changed my mind after that. Finally, we come to advanced skills. This is already a long video, so I'll keep it short here since I don't have much to say about these. The fact is, I can't even really speak to most of these topics because I've never learned them myself. I may have encountered them in a single talk, or it may have been mentioned as a single sentence in a lecture, but I'll do my best to give you a brief taste of what advanced statistics look like. When it comes to learning more advanced areas of statistics, what you're really dealing with are more complex forms of data. Spatial data, survey data, functional data, high-dimensional data, etc., etc. These are not like well-behaved IID data that you would encounter regularly in your coursework. It follows that since this data is much more complex, the statistical tools need to become more complex too. I'll use causal inference here as an example because it's growing more and more important in biostatistics. Causal inference deals with the analysis of observational data. Data where we can't control the value of the independent variable. When we can't control the independent variable, it enables other variables called confounders to pollute the relationship between our variable of interest and the outcome. It's hard to know exactly what the cause and effect relationship would be. if there is any. So methods from causal inference essentially try to remove the influence of these confounders, making statistical associations closer to true cause and effect relationships. That was 7 years of statistics in 25 minutes. If you're thinking about going to grad school or you're just self-studying statistics, I hope I've given you a better idea of what you're getting into so that you can better set yourself up for success. If you enjoyed this video, then I hope I've convinced you to subscribe for more content like this. I can't believe I finally get to say this, but the channel has finally reached 100,000 subscribers. This is the first video I've written after reaching 100K, so thank you all who have helped me to get to this point. It's a long way to 1 million, and I have a lot of ideas for statistic content in the future, so I hope you'll stay tuned. To get updates right in your inbox, I hope you'll also subscribe to the channel newsletter. That's it for this one. See you in the next one.